A star burns brightly for billions of years, until one day it collapses and explodes in a burst of energy so intense it can outshine an entire galaxy. This explosive event, known as a supernova, doesn't just mark the death of a star, it creates the very elements that make up planets, stars, and even life itself. What happens during those final moments? How do these fiery explosions shape the universe around us? And why are they crucial to our existence on Earth? In this video, we'll dive into the science of supernovae, uncovering how these cosmic blasts not only bring an end to stars, but also trigger the creation of everything from the building blocks of planets to the atoms in our own bodies. A star is essentially a massive ball of gas, mostly made up of hydrogen, constantly undergoing a process called nuclear fusion. During fusion, hydrogen atoms collide and merge to form helium, releasing immense amounts of energy. This energy is what makes stars shine, and it keeps them burning for millions, even billions of years. But just like anything with a limited fuel supply, stars eventually reach the end of their life. Smaller stars, like our Sun, burn through their fuel more slowly and end up as white dwarfs, a dense, fading remnant. However, much larger stars, at least 8 times the mass of the Sun, live much faster, burning through their fuel at a rapid pace. When they run out, they can no longer withstand the gravitational pressure pulling inward. This causes a spectacular collapse, followed by a violent explosion known as a supernova. This explosion is so intense that it sends out shockwaves of energy and elements, scattering them throughout the universe and enriching the cosmos with the very building blocks that form planets, stars, and even life. As a massive star reaches the end of its life, its core starts to change. For billions of years, the star has been turning lighter elements like hydrogen into heavier ones, which keeps it shining. But towards the end, the core begins fusing even heavier elements like carbon, oxygen, and iron. The problem is, once iron is formed, it can't produce energy like the lighter elements can. Without this energy, the star can't hold up against its own gravity, causing it to collapse. As the star's core collapses, it does so with unimaginable speed, compressing in mere seconds to a size smaller than Earth's radius. During this collapse, protons and electrons, which usually repel each other, are forced together by the overwhelming pressure. They combine to form neutrons, and in this moment, the core becomes an incredibly dense neutron star. The collapse is so intense that it sends shockwaves through the star's outer layers. These outer layers, once supported by the core's pressure, now fall inward, but the rapid collapse triggers a violent rebound, sending the outer layers flying outward in a massive explosion, or what we call the supernova. A supernova is one of the most powerful events in the universe. Within moments, the explosion becomes brighter than an entire galaxy, outshining billions of stars. The energy released is staggering, about as much as the Sun will release over its entire lifetime, all packed into just a few seconds. This explosion not only marks the end of the star, but it also creates and disperses heavy elements like gold, uranium, and iron, which are essential for the formation of planets and life. These elements scatter across space, seeding new stars and worlds, and contributing to the ongoing cycle of cosmic creation and destruction. A star that once shone steadily for billions of years leaves behind a legacy that will shape the universe for billions more. After the spectacular explosion of a supernova, the universe is forever transformed. The shockwave from the explosion releases immense energy, sending ripples through space and marking the end of one cosmic chapter. The fate of the star's core depends on its mass. If the core is small enough, it survives the explosion and becomes a neutron star, an incredibly dense object roughly the size of a city, but with a mass greater than the Sun. A neutron star is so dense that a single teaspoon would weigh as much as a mountain, and its intense gravity distorts time and space around it. One of the most fascinating phenomena of neutron stars is their pulsar behavior. As the star spins rapidly, it emits beams of radiation from its poles, creating a visible pulsating effect across vast distances in space. However, If the core is massive enough, typically at least 20 times the mass of the Sun, gravity wins. The core continues to collapse under its own weight, eventually forming a black hole, an incredibly dense point in space with such a strong gravitational pull that nothing, not even light, can escape. This marks the creation of one of the most extreme and mysterious objects in the universe, a place where our understanding of physics breaks down. Meanwhile, the outer layers of the star don't just disappear. They form a nebula, a vast cloud of gas and dust that, over millions of years, condenses to form new stars and planetary systems. These stellar nurseries are some of the most fascinating places in space, where the raw materials for new solar systems just like our own are born. Humans have been lucky enough to witness supernovae with the naked eye throughout history. One of the most famous supernovae occurred in 1054, when a star exploded so brightly that it was visible during the day, even though it was far away. The explosion left behind the Crab Nebula, a glowing remnant of that event that we can still see today through telescopes. Fast forward to modern times, astronomers are using powerful telescopes to observe supernovae as they happen in distant galaxies. With technology allowing us to witness these cosmic explosions in real time, we can learn more than ever before about the life and death of stars. But what's even more exciting is that scientists believe a nearby star, Betelgeuse, could explode in the next 100,000 years. While that may seem far off, it reminds us that the universe is full of unpredictable and incredible events just waiting to happen. Supernovas are not just awe-inspiring explosions. They are one of the reasons we exist. Every atom in your body, from oxygen to iron, was formed in a star that exploded billions of years ago. Without supernova, there would be no Earth or life. These explosions release energy equal to the Sun's entire 10 billion year output, scattering essential elements like carbon, oxygen, and iron across the universe. Scientists study supernovas to understand how these elements spread, measure the universe's expansion, and explore extreme objects like black holes and neutron stars. In short, supernovas are cosmic recycling engines that help unlock the deepest secrets of space. Though we may never directly witness the explosive death of a star, its impact is deeply woven into the fabric of our existence. From the very atoms in our bodies to the formation of planets and life itself, supernovae play a vital role in shaping the universe we know today. These cosmic events, though destructive in nature, are also the birthplace of the elements that make life possible. As we continue to study the aftermath of supernovas, we unlock deeper insights into the vast mysteries of space, while gaining a profound appreciation for how interconnected we truly are with the universe. Thank you for joining us on this incredible journey through the explosive life cycle of stars. If you enjoyed exploring interesting stories with us, don't forget to hit that subscribe button. What topics do you want us to dive into next? Let us know in the comments. Join us as we get animated about science here at Animated Science.